Hey guys, so today we're going to talk about testing means and t-tests. This is the first time that we're going to get into inferential statistics, which is definitely my favorite material in the course. This is where you'll be applying math to answer research questions. And we're going to specifically work on research questions around evaluating means. So first of all, to start, thank you for those of you who did fill out the survey. Two big takeaways so far were to do more practice questions and have more images on the slides that we'll go through because those have been very helpful for building an understanding of the content. So to start, we're going to do some questions from what we learned last class, which was probability. We'll do some practice questions together. And then we're going to get into t-tests, which is one of the main ways to test the differences in means. And there's a few different ways to do it. So we'll start with one sample t-test, which is kind of the base approach. And we'll use that approach to go over the intuition behind a t-test and what it all means. And then we'll go over two other approaches for slightly different sorts of tests. So let's start with some probability questions. We talked a lot about two examples last class, mainly flipping a coin and drawing from a deck. Let's start with flipping a coin. What is the probability that you get at least two heads when you flip a coin? What is the probability you get two heads in a row when you flip a coin twice? So you might remember, and if not, definitely look through the probability slides where we talk about independence. One great feature of independence is that when you want to calculate the probability of two events that have no effect on each other, in other words, are independent, like flipping a coin twice, you simply multiply their respective probabilities. So the probability of getting two heads if I flip a coin twice, well, the probability of the first coin being heads, if it's a fair coin, would be a half, and the probability of the second coin being heads, if it's a fair coin, would also be a half. I multiply those two together, and the probability of getting all heads in two flips is just a quarter. This other question is a little trickier. So this time there are three flips involved, and I want you to think about, with those three flips, what are the chances that I get at least two heads? And I'll give you a hint while you think about it. It's going to be really important that you enumerate the sample space. So the first thing I want you to realize is this is actually talking about several different outcomes, right? Because I could get 2 out of 3 heads in a lot of different ways. One is I could get 3 heads. Another is I could get 2 heads and then a tails. Another is I could get heads, tails, heads. Another is I could get tails, heads, heads, right? And all 4 of those outcomes make up this event of at least 2 out of 3 heads. So let's start with the first outcome of 3 heads. We know what the probability of that is. Because they're independent events, we multiply the probabilities of each respective event. So the first one being heads is a half, the second one being heads is a half, the third one being heads is also a half. We get a probability for that event of 1/8. And you're going to see a pattern emerge as we go through, of that outcome of 1/8. And you're going to see a pattern emerge as we go through these other outcomes. So let's now do the outcome of first I get a tails and then I get 2 heads. Well, the probability of the first coin being tails, if it's a fair coin, is a half. The probability of the second coin being heads is also half. The probability of the third coin being heads is also half. Multiply those 3 together and I get 1/8 again. And hopefully by now you realize this pattern. The probability of tails and heads is the same. The order doesn't really change anything. So each of these 4 outcomes that I've delineated, where I'm getting at least 2 out of 3 heads, have a probability of 1/8 of occurring. So the probability of getting at least 2 out of 3 as heads, I just add them all up. So heads, heads, heads is 1/8. Tails, heads, heads is 1/8. Heads, tails, heads is 1/8. and then heads, heads, tails is 1/8. So each of those 4 outcomes have a probability of 1/8. Altogether, the probability of getting at least 2 out of 3 heads is 1/2. Which is a little bit unintuitive because you're talking about 2 out of 3 being heads, but with a fair coin, this is functionally the same as flipping a coin once and seeing if it lands heads in terms of probability, right? The experiment is different, the sample space is different, but in terms of probability, it's still 1/2. Now let's talk about this other example of drawing from a deck. So I want to know the probability that I get 2 spades. So this is a little different than coin flips. I want you to think about why it's different, and then let me know what that probability is. I'll give you some time to think about it. So hopefully you realize the big difference here is we no longer have independence, right? Unless I'm replacing the card in the deck, which I didn't tell you I was doing, the probability of the first card being heads of being spades is 13 out of 52, right? Because a deck has 52 cards and it's split evenly into 4 different suits. So I have a 13 out of 52 chance of getting spades on my first draw. However, my second draw, and you might remember this if you look through your notes on probability, the probability of dependent events, I can't just multiply the 2 events. What I have to do is I take the probability of the first event and then multiply it by the probability of the second event, given that the first event occurred. So it's similar. I'm still multiplying 2 probabilities, but the interpretation behind the second probability is different. So we all agree the first card is 13 out of 52 because there's 52 cards in the deck and it's evenly split between 4 suits. So we have 13 out of 52 chance of drawing a spades. The probability of the second card also being a spades is no longer 13 out of 52. There's only 12 spades left because I took one in the first draw, and there's only 51 cards left. So what I would do to get the answer to this first bulleted question is 13 out of 52 times 12 out of 51. And the interpretation, again, is slightly different because it's the probability of getting a spades and then the probability of getting a spades on the second draw, given that my first draw was a spades. So still multiplying 2 probabilities, but different interpretation. Now I want to talk about getting 2 probabilities, the probability of getting 2 of the same card. And what I mean here, I'm not talking about the same suit. I'm talking about the same number, or in the event that it's one of the cards with a face, like a jack, king, queen, the same card of a different suite. So in other words, if the first one is a jack, then the second one should also be a jack. If the first one's a queen, the second one should also be a queen, and so on. Just obviously it'll be a different suit because there's only 4 suits in the deck, and there's only one of each suit, so you can't draw the exact same card twice if we're talking about a single deck. So take some time to think about this. I'm confident you can get it on your own, although it might be a little tricky when you think about it, and we'll talk about why in a minute. So let's talk about that first card. These events are not independent, so I have to follow the same structure as before, where I take the probability of the first event multiplied by the probability of the second event given the first event. So the probability of the first event, I don't really care what the first card is, right? It could be anything. I only care what the second card is, so the first draw is irrelevant. Whatever happens, happens. We could treat that probability as 1. I'm okay with a 2 of spades. I'm okay with a jack of hearts. I'm okay with a 10 of diamonds, right? All of those still allow me to get for the second event to be the same value card, not the same suit, but the same value card. So we're going to treat the probability of the first draw as just 1. Now the probability of the second draw being the same value, again, not the same suit, but the same value, is going to be what? right? And we know anything times 1 is itself, so this second probability is going to give me the answer because it's going to be 1 times this probability. So given that the first card was the value I wanted, how many cards of that value are left? Well, just 3. For example, if I drew the 2 of hearts, there's only a 2 of spades, 2 of diamonds, and 2 of spades, diamonds, hearts, and clubs left. So I have those 3 left, right? So I have 3 left, that's my numerator, and my denominator out of all the possible outcomes, how many cards are there? Well, there's no longer 52 because don't forget, this is given the first event, and the first event took 1 card out. So it affects both the numerator and the denominator, right? There were 4 2s, now there's only 3, and there were 52 cards, now there's only 51. So I get 3 out of 51. 1 times 3 out of 51 is just going to give me 3 out of 51. And you should always simplify. 3 and 51 do have a common factor of 3, so I can simplify this to 1 out of 17. So the chances of getting a pair, if I draw exactly 2 cards, is 1 out of 17. So those are just some examples of probability to get you thinking about how this can apply. And I appreciate you guys asking for more practice questions. I think that's a good way to learn. And that's why the homework and quizzes are so important, because you're applying the concepts that we cover in lecture. All right, so now that we've done some practice questions based on last lecture, we're going to dive into today's material, which is statistical inference, the first of statistical inference. Like I said, my favorite topic in this class, because this is where you're applying what you've learned to answer real questions. That's not to say the other topics aren't also important. The way in which you apply it is critically important, as we've talked about, but this is the math of how it's applied to make inference about your population. So I threw out an example here. What is the average SAT score of Virginia Tech students? According to U.S. News, we know the answer. It's 1330. That's the average of Virginia Tech students. However, let's say I'm a skeptic. I don't quite buy it. I want to conduct my own test to figure out if that's true or not. This mathematical notation might be a little intimidating, but it's actually very simple in what it's relaying. This right here is the null hypothesis, and this is known as the alternative hypothesis, which you'll see written in 2 different ways. Sometimes you'll see it with the subscript A for alternative. Sometimes you'll see it with the subscript 1, because the null is written with a 0. So it's written with a 1. I'm going to use an A in this course because that's the way I was taught, but you should know that when you see it with a 1, it stands for the same thing, the alternative hypothesis. So the null hypothesis is usually written with an equal sign. So the null hypothesis here is U.S. News' claim is true. The average SAT score of a Virginia Tech student is 1330. Whereas the alternative hypothesis is that it's not equal to 1330. It's something different. Now here you'll see a very similar set of hypotheses, but they're written differently. And I wanted to go over this as well. So sometimes people aren't just interested in, is it different? Like in this set of hypotheses, right? Here I'm saying it's 1330. I want to know if it's anything besides that. Sometimes people's research question is more specific. Like let's go back to the example of I'm a skeptic and I want to see if U.S. News is reporting this accurately. And based on my experience at Virginia Tech, students seem very smart. I think that the average SAT score is actually higher than 1330. So I'm not interested in testing an alternative hypothesis of not equal to. I specifically want to know, is it greater than 1330? And that implicitly includes less than in the null hypothesis. Sometimes you'll see this kind of hypothesis, these pair of hypotheses written with an equal sign for the null and a greater sign for the alternative. Even when it's written that way, even when you have mu equals 1330 as your null and mu greater than 1330 as your alternative, it is implied that anything less than 1330 is part of the null. So I think it makes more sense to be explicit and write it in this format. However, some people will write the null in this format, even when they're testing. This is referred to as a one-sided alternative hypothesis, and it's one-sided because I'm specifically interested in one direction, which is greater than. Now I have a question for you to think about. All of these hypotheses reference mu, and then the constant 1330. We know where 1330 comes from. That's our, base of knowledge. That's what we're trying to prove or disprove. That's the current standard. Why mu and why not x bar? They're both forms of the mean. Why am I always writing the hypothesis in terms of mu? So hopefully you guys remember, while they are both means, there is a significant difference in the interpretation behind mu and x bar. Mu corresponds to my population mean, whereas x bar is my sample mean. I know my sample mean, and I know due to random variation, it might not be equal to my population mean. But what am I trying to answer here? I'm trying to identify the truth. Are SAT scores different than 1330, right? So some variation in my sample doesn't definitively answer that question. The question I'm answering is related to the population parameter mu, right? I will use x bar in my test statistic, as you'll see in a future slide, but what I'm testing is for the truth, right? And I'm going to use my sample data to do that. However, when writing my hypothesis, it would be silly to say, well, x bar is greater than 1330, therefore the alternative is false, because there's going to be some amount of deviation and spread, and the test statistic, as you'll see in a future slide, is measuring if that's a significant amount of deviation. All right, so this is this test statistic we're going to cover. I want you to look at it. This is known as the T statistic. I want you to look at it and compare it to the Z statistic, also known as the standard normal. And hopefully you notice it looks really similar, right? If I were to replace the T with a Z, the only thing that really changes is this S over the square root of n becomes sigma over the square root of n. And to be even more pedantic about it, Z is generally written as X, not X bar. So it's X minus mu over sigma. And there is no square root of n. That's how we normally write Z. But the distribution of X bar is a little different. And this is what the central limit theorem was somewhat getting at, is the distribution of X bar, its standard deviation is S over the square root of n, or actually sigma over the square root of n. So if I were to replace this with a sigma, this would be a Z statistic. This would be a standard normal, because the standard deviation of X bar, and you can prove this mathematically, is sigma over the square root of n. So if I knew sigma, I could write this as Z. However, we rarely know sigma in practice, so let's not make assumptions that we don't have a solid basis for, and let's use the sample standard deviation S, and that just changes it from the standard normal Z to the T. And I have this picture here kind of going over the difference between the T and the standard normal. Oh, sorry about that. So here's the standard normal in light blue, right? And you could see the T distributions, which are the different colors, all follow the same shape. They're all symmetrical, they're all bell curves, but they are all slightly different. Specifically, the tails are all higher, right, than the standard normal. And because the area underneath it is 1, if the tails are higher, that tells you that the mode, also known as the peak, is going to be lower. And what I want you to notice is how the T varies based on the degrees of freedom. So here we have a T with 1 degree of freedom, and we're going to talk about what degree of freedom means in a second. So the T with 1 degree of freedom is most different from the standard normal, right? The tails are the higher, not by a huge amount, but higher than any of the other t's. And the mode is lower than any of the other t's relative to the standard normal. Then as we move to 5 degrees of freedom, which is the one in the red, it looks very close to the standard normal. And as we move to 10, it's almost on top of it. And as we move to 30, it basically is on top of it. You can't even really see purple. It's like sandwich in between blue and green, because as the degrees of freedom increases, you approach the Z distribution. So the T and Z are very similar in shape and size, especially as your degrees of freedom increase. And 30 is kind of that cutoff point where you could just look at a Z because there's not a huge difference between the two. And I think I mentioned this to you before when we were talking about why people use 30 as the arbitrary cutoff for the central limit theorem. And this is why, because when you don't know sigma, right, you don't have a Z, you have a T, and the difference between the T and the Z goes away when your degrees of freedom is roughly 30. Now let's talk about what that degrees of freedom is. It's nothing but your sample size minus 1. That's all it is. You'll sometimes see it written with a V. That's actually the Greek letter nu, but it looks like the letter V as well. So you'll sometimes see it written with a nu or a V, whatever you want to call it. That is your degrees of freedom, and it's nothing but your sample size minus 1. And we could get into more detail about the sample size minus 1, but we talked a little bit about the intuition behind it, is that we don't know one of the parameters and we're estimating it, so we take one away when calculating the degrees of freedom. So that was a lot of information. To recap, this is a statistic we use to calculate differences in mean, and we'll go into more detail about how we calculate it from the statistic in the next slide. And we do that by looking at this t distribution, which again you're going to see in more detail on the next slide. So let's talk a little bit about hypothesis testing. Here you have a series of hypotheses. In this image, they don't use alternative like I did. They use 1 for the alternative. And you're always comparing to 23. And I like that they were explicit here, where when you're doing a one-sided test, the other side is implicitly and explicitly stated as part of the null hypothesis. So take a minute to look at this picture, and then I'll talk about the title, which I realize is pretty intimidating in terms of the mathematical notation, but it's actually a very simple concept once we go through it. So the idea here is we want to reject the null hypothesis. We want to say it's not true in the event that P, and we'll talk about what P means, but it's this intimidating looking notation, is less than alpha. Now alpha is an arbitrary value, which we're going to go into more detail in a future slide, that you set as the statistician, and it kind of represents the level at which you are okay with making a certain type of error. And I know that's vague, but more generally, the higher alpha is, the easier it is to reject the null. The lower alpha is, the more evidence you want against the null in order to reject it. So let's just look at these types of tests, and then we'll talk about this notation for P. So here we have the null and the alternative, right? So this is the null distribution. It is centered at 23. So if I were to get a value like 23.1, let's just say that's over here, or somewhere over here, I'm not going to reject H sub O. But if I get something more extreme, significantly more than 23 or significantly less than 23, I am going to reject H sub O, also known as the null hypothesis. And in this case, because there's two ends of the curve at which I could reject, that's why this is known as a two-sided or two-tailed test. I split alpha in two so that my total alpha area the total area during which I reject is alpha, right? Because I do alpha over 2 plus alpha over 2. The one-sided test is easier. You don't have to do that, right? I'm only looking at cases where it's less than. So I put my entire alpha area over here, and I reject in the event that I observe something extreme on this side. I know this is a little vague at this point. We're going to go into more detail about how these statistics are calculated. So let's start by looking over here. What is P? How do we calculate it? Alpha, I already told you, is kind of arbitrary. There is a standard, which is 0.05. Why is 0.05 the standard? No particularly good reason. People just liked the number 5 for a lot of reasons. It's a round number in our number system, in the Arabic numerals, and people are okay with making an error 1 out of 20 times, and we'll talk about those errors in more detail later in the slides. P, on the other hand, you calculate from your T statistic. So these absolute values, I put these here because T, remember, like your standard normal or Z, can be negative or positive. And technically this isn't quite true without the absolute values being there, but let's ignore them for the sake of simplicity right now. What this is saying is P is the probability, remember that's what big P means, that my T distribution is greater than the T statistic I calculated. This OBS just stands for observed, the T statistic that I observed in the data I collected. So if I observe a T more extreme, what's the probability of getting a T more or as extreme as the T I observed? And a matter of fact, I'm realizing right now this could have an equal sign here. It's not necessary because it's continuous, but for clarity, I think it makes sense to put an equal sign there. So P is simply, to restate that point, the probability of observing values in the T distribution as extreme or more than what I saw in my data. And the absolute value here again is for this two-sided test. So like if we assume this is centered at 0, which it is according to the T statistic you just looked at here, because remember under the null, X bar should be centered at mu. So if we assume this is 0, right, the absolute value is saying, let's say my T is here, it's going to calculate the probability of observing anything here, meaning less than that, negative T, or it'll be symmetrical, so it'll be roughly here, anything greater than that positive T. So like the absolute value does make the notation more complicated, but it's really just to convey this idea of more extreme or less extreme, because our distribution can be either positive or negative. So like for example, you don't need the absolute value in the event of a left-tailed test, right? Because all I want to know is observing a T less than what I observed. So this sign would flip, right? And I would say, if I observe something here, I want to know all the area under the curve that's less than that point, right? And that's my p-value. And you could see here, p is clearly greater than alpha, but if I observe something over here, right, p is just going to be this area, and it's going to be less than alpha, right? And then I think this is the easiest one to see, is the right-tailed test. So if I observe a T, let's just say it's perfectly centered right at the middle, right? I know this is going to be 0.5, this is going to be my p-value because it's half the distribution is to the right, but I want to know T greater than what I observed. So this is what I observed plus everything bigger than it, and that's going to be 0.5. So these are just some examples. I know we still haven't gone into actually calculating it. I promise we have an actual question where we're going to do this next lecture, and we're going to go through in more detail during this lecture. Hopefully it's starting to click. We'll make more connections as we go through the lecture. Okay, so the first thing I want you to think about is, based on what I told you, and I know we kind of circled around and had a few different tangents and way of looking at it, how would you interpret a p-value? All right, so we know what the t is. It's a lot like the standard normal, especially if my degrees of freedom is close to 30. But how do you interpret the p-value? And I'm going to flip back to this slide while you think about it, where p is defined as the probability of a t more extreme than what I observed. So this is a really important concept in statistics. The idea behind the p-value is it's the probability of observing your data, and I'm going to flip to the next slide because I go through it here. The probability of observing our data, or more extreme, under the null, right? So we assume the null is true, and then we say, given that the null is true, what's the probability of getting this set of data? And hopefully now alpha is making a little more sense to you, because, right, if this is the null distribution, right, this is a t distribution, let's just say this is the null, observing a data point here or more extreme is alpha over 2, right? Or, I could include this if this is a two-tailed test. Let's just look at the one-tailed analysis. It's less to think about. But in this distribution, right, I'm going to tend to observe stuff under the mode. I'm going to tend to observe stuff near here, near the center. That's where most of the data lives. But I could observe something over here. And I could observe more extreme things moving in this direction. So alpha is kind of the cutoff of saying there's an alpha chance that I would have observed that under the null, but that's so you want to pick alpha to be relatively small and small enough such that you say it could have happened, but it's smaller than what I expect to have happened. And we'll talk more about the types of errors in future slides. This is the intuition behind a p-value. It's the probability of what you observed, or more extreme, assuming the null was true. And because that probability ducks alpha, you will reject the null. And we're going to talk more about what that means right now. So the other thing I want to be clear about is that p-values are a measure of statistical significance, not practical significance. And we talked about this in previous lectures, right? Practical significance is this meaningful? Is this difference meaningful, right? Does it tell me something? Is there a meaningful, impact I can make? Or, I know the value is different, or I believe the value is different because p ducked alpha, but is that difference going to matter? And then the other thing I want to know, and this is a little bit outside the scope of this class, is that it can be a function of sample size. As you collect more and more data, your ability to detect smaller and smaller differences increases. And again, we're getting statistical significance, not practical significance. So again, it's really important to not just report out your p-value, but also report out the measure of that difference. And especially when you have a test like this, a two-tailed test where you're comparing a singular point to a range of points, right, this becomes especially problematic. Again, this is a little bit outside the scope of the class, but it's just something I wanted to point out because I think it's interesting. So these are just some limitations to be aware of with p-values. This is the literal interpretation of a p-value, and I italicized or more extreme under the null. And then I wanted to talk a little bit about the type of errors. So here as columns, you have your two kind of scenarios. Either your null hypothesis was true or it was wrong. And we don't know whether it's true or wrong, but let's just say we assume, in this column it was correct, in this column it was false. Now, the outcome of your test, if p does duck alpha, you're going to reject your null, right? If p is greater than alpha, you're going to fail to reject your null. And the interpretation there is kind of nuanced. When you fail to reject your null, you don't necessarily accept it. You just say, I don't have evidence that it's wrong. So it's a little different than accepting, and to maintain good practice as a statistician, you will say, I fail to reject the null. You won't say, I accept the null. So it's a little nuance, but it is an important difference in interpretation. So remember, if H of O is true and I reject the null, I made a mistake. That is an error. And the probability of that error occurring is equal to alpha, right? When I set alpha, And remember, the standard is 0.05. That means there's a 5% chance of observing that data are more extreme under the null. So 5% of the time, I'm going to reject the null even though it was actually correct. And that's your error rate is equal to alpha. So it's very easy to remember. On the other hand, if H of O is true and I failed to reject the null, I made the right decision. That's why this is colored in green. And that's going to happen 1 minus alpha percent of the time. So if alpha is 5%, that's going to happen 95% of the time. Now let's talk about the other kind of good scenario is the null was incorrect and I rejected it. That's going to happen 1 minus beta percent of the time, and that's also a good outcome, right? If the null is incorrect, I should want to reject it. What's beta, you're probably asking? That's a little bit outside the scope of this class, but you could think of it as the other type of error. So alpha is the error you'll make where you reject the null even though it was true. Beta is the error you make where you fail to reject the null even though it wasn't true. So that's the other type of error you make. And 1 minus beta, also known as power, kind of measures your ability to reject the null when it is false. And it's not something you could calculate directly. You have to make assumptions about that alternative distribution. And it is something you will learn if you take more advanced statistical courses. So, okay, that's a little bit about the intuition behind p-values and hypothesis testing using the t-statistic. I know that was a lot of information. I'm going to do a quick recap, and then we're going to go over alternative formulations of the t-statistic to test different types of things. So first, let's recap what we summarized here with hypothesis testing, right? The null is where the equal sign will go. Sometimes you'll see it as including the inequality opposite the alternative. Sometimes you'll see it as just an equal. But the equal sign always goes in your null. And then your alternative is what you're testing it against. So is the average SAT score not 1330, or is the average SAT score greater than 1330, are two types of alternatives. This is a right-tailed alternative. This is a two-tailed or two-sided test. And you're always testing your population parameter. Here's our t-statistic. We like this statistic because it lets us take our data and convert it to a distribution we know pretty well, which is the t-distribution. And you also hear people refer to it as the student's t-distribution. Just an interesting side note is that's because the statistician who uncovered this distribution at the time couldn't publish under his name because he was working for a company and another statistician, Guinness actually, funny enough. And so when he published his work, he just referred to himself as student. And that's why this is sometimes called the student's t-distribution. So the t-statistic kind of lets us take our data, specifically our mean, and convert it into a statistic whose distribution we know. So we take our mean, we divide by the mean's standard deviation. Because we don't know the true parameter of the standard deviation, instead of a z distribution, it's a t distribution. Although it does look a lot like the z distribution, especially as n increases. Okay, so let's talk a little bit more. Let's recap a little bit about hypothesis testing. The idea is you set an alpha level, typically 5%, but if you're testing something that's more widely believed, you better have more evidence to reject it, and you maybe a lower alpha of like 1% or 0.1% is warranted. On the other hand, if you're testing something that you don't have a ton of evidence for, you could use a higher alpha, like 10%. So it is a little arbitrary, this distinction of what you set alpha as. But like I said, the typical measure is 5% for no good reason. There's not a big difference between 5% and 6% besides that 5% is just like a comfortable number in the Arabic number system that we use, which has 10 digits. So, and then you calculate your p-value, which is based on your t-statistic, and you say, looking at the t-distribution, how many t's are more extreme than the t I observed? What area under the curve? Look at all the values of t that are more extreme that I've observed. Calculate the area under the curve. And in the event that it's two-tailed, you look on both sides, which is pretty easy because it's symmetrical, so you can just look at one side and multiply by 2. Or in the event of a left-tailed or right-tailed, you just look at the density to the left or the density to the right, respectively. And we talked a little bit about the types of errors, which I think is important to know, even if it is a little bit outside the scope of the class. So alpha is your type 1 error. You'll sometimes hear people refer to it as type 1 error. I think in the computer science domain, they'll refer to it as alpha and beta. But in the statistical domain, we sometimes say type 1, type 2. So alpha is my type 1 error, which is I reject a null even though it was correct. And then my type 2 error is exactly the opposite. I didn't reject the null even though it was wrong. And I do want to, again, repeat this point about statistical significance because it is really important, right? The p-value is measuring, does a difference exist? It's not measuring, is that difference practically important? And you calculate that p-value, like we said, by looking at your known distribution, in this case a t-distribution. We'll talk about other statistics in the future, but in this case a t-distribution, and saying what's the chances that I get something more extreme than what I observed, calculating that with my data. And then these are your two happy paths, which you could calculate as 1 minus alpha, 1 minus beta. I say happy path not in the sense of computer programming and that it's the straightforward case, but happy in the sense that you like this outcome, right? If h of o is not true, or if h of o is true, you don't want to reject it, and if h of o is untrue, you do want to reject it. So these are not errors, whereas alpha and beta do represent errors. And then, if this table is kind of challenging to remember alpha you set. So alpha is the probability that you are comfortable with rejecting h sub o even though it's true. And then remember, each column sums to 1, right? That's a rule of probability that we covered last lecture. Everything in the whole sample space covers 1. So if h of o is true, these two outcomes make up the entire sample space. In fact, they're complements, to use a concept we covered last lecture. If h of o is true and we reject h sub o, or we fail to reject h sub o, right? Those are the only two possible things we're going to do. These two things have to sum to 1. Same thing here, right? These two things have to sum to 1. So it's really easy to recreate this chart when you think of it that way. All right, now let's talk about different types of t-statistics. And I know this is super intimidating. I know the notation is very intense. But again, it is more complicated than what we just did, but it's not as complicated as it looks at first glance. So let's talk about, this is sometimes referred to as Welch's test. You don't need to know that, it's just the statistician it's named after. But the idea here is you're comparing two samples. So you have groups and you want to know the difference in the means of the two groups. So one example might be, do student athletes perform better on the SAT than those who are not athletes? And I bring that up just because it's related to our first question when we were talking about hypothesis testing. But here, there's just a constant because I'm not comparing two groups. I'm just looking at one group, right? And is that one group different or not? Here, when I'm looking at two groups, I have two sets of means, and I want to know if those means are different. So the null hypothesis, take a minute, tell me what you think the null hypothesis would be. Obviously, when I'm looking at SAT scores, just to preface this a little bit, right, it's not quite the same for everybody, right? Some people have other impressive accomplishments, and the admissions committee might, weigh those accomplishments more heavy than their performance on the standardized tests like the SAT. So student athletes obviously have some impressive accomplishments, and you would think maybe the admissions committee, weighs that a little more heavily and doesn't require as high an SAT score as a result. So this is just, I'm making this up, but this is like one example of comparing means between two groups, the two groups being athletes and non-athletes. So take a minute, let me know what the null and alternative look like here. So I think there's a few ways you could write it, and the stat does kind of give it away. So obviously they split the groups into A and B. Let's say A is athlete and B is non-athlete, just so that the letters kind of correspond. So you could write it as mu A equals mu B. You could write it as mu A minus mu B equals 0, right? Those are both valid ways to write the null, that there is no difference between student athletes and athletes on their SAT performance. And then the alternative, I could see an argument for doing it one directional, I could see an argument for doing it two direction, but the idea would be mu A is not equal to mu B, or mu A is less than equal to mu B. So those are two alternative ways you might write it. So let's look at the statistic. It's very intimidating, but it's not as bad as it looks, I promise. First of all, recognize that this mu A minus mu B, the way we've defined a hypothesis is 0, right? Because under the null, mu A is equal to mu B. So mu A minus mu B is 0. You could erase this whole thing from the t-stat. And in fact, a lot of times, if you look up a two-sample t-test or you look up Welch's t-test, they won't even write this because they assume it to be 0. I did include it just because sometimes you want to test, is the difference in means between the two groups greater than or less than or not equal to some constant, in which case the constant would go here. So I wrote it to be more generalizable. However, 90% of the time when you do a two-sample t-test, this is going to be 0 and it's just going to drop out. Now this is the difference between means between the two groups, athletes and non-athletes. This is pretty intuitive as far as where that comes from. The numerator also looks intimidating, but the more you look at it, the less intimidating it becomes. In fact, it probably looks really familiar. Let's just cover up this term right here and look at over here. So if you distribute the square root, you're going to get the standard deviation of group A over the square root of the sample size of group A, which is exactly what we had in our previous t-statistic. The difference here is because there's two groups, there's two different standard deviations, and what you're doing here is you're pooling the standard deviations and you're weighting them by the size of the groups to calculate kind of like a pooled standard deviation. That's a little bit of the intuition behind what's going on with Welch's test. And so this is like some measure of spread of deviation, which if you cover up one of the fractions is something you've seen before, but with both fractions you're kind of trying to weigh the deviations within each group to create one pooled measure of deviation, of standard deviation. So again, all you're doing is you're taking the variance of group A over the sample size of A plus the variance of group B over the sample size of B, and then taking the square root, because remember we always want it in terms of standard deviation, not variance. Sorry about that. Now what's going on over here? Okay, this is a lot, but you don't need to know this. It's outside the scope of the course. However, some of your project ideas did mention comparing means between two groups, especially those of you looking at relationships between qualitative and quantitative variables or categorical and numerical variables. So I wanted to share this with you. The degrees of freedom is different when you do Welch's two-sample t-test. It's no longer n-1, which kind of makes sense because you have two n's here. So how do you handle that? Well, this is the formula you use. And I know it's a lot. You don't need to know it. Feel free to plug it in if this is relevant to your project idea. Very few people have this memorized, myself included. I did at one point. I don't know if I still do at this point. But the idea here is it's kind of similar to the intuition I was explaining here with like a pooled variance to calculate the degrees of freedom, which you might remember is the Greek letter nu, although it looks like the letter V. Okay, so that was a lot, but this is an alternative formation of the t-statistic to calculate the difference in means, and this is the associated degrees of freedom. Why do you need to know the degrees of freedom? Well, let's go back to our chart. To calculate this density and then the area of things more extreme or not, you need to know the degrees of freedom, because as you saw over here, right, the density curves look different based on the degrees of freedom. So, for example, let's say I get a t-statistic of -2, right? Over here, that corresponds to this whole area, assuming that my degrees of freedom are 1. But if my degrees of freedom increase to 30, right, it's this area. It's a much smaller p-value. So that's why you need to know the degrees of freedom. Okay, now let's talk about this. This is a kind of a complicated way to compare the difference in means between two groups. Now let's talk about a paired t-test. Here I'm still comparing differences in groups, but there's a huge difference. In fact, you see this little subscript D on all my statistics. Otherwise, this looks exactly the same as the t-statistic I showed you before. The degrees of freedom is the same. The only real difference is the subscript D. So I want you to take a minute and think about what that subscript could possibly mean. So the idea here is we're looking at differences. So you're pairing each of your responses, and this isn't as appropriate for the example I gave before, but I'll give you a better example. Let's say I'm evaluating the effect of some intervention, we'll say it's medicine, and I test students. I have students study under a placebo and then with the medicine, and I randomize the order to avoid, learning effect and other forms of bias. And now I have, student 1, how they did under the placebo, and student 1, how they did with the help of medicine. And I subtract every student's differences, medicine minus placebo typically, because I'm assuming that the medicine is improving and that'll give me positive values on average. Those differences are what I'm taking the mean of. And then my null, I'm saying what is the assumed difference. So like the null hypothesis here would be that there is no difference, mu d equals 0. The alternative hypothesis, again, you could argue for two-sided or one-sided, but I think in this case I'm most interested in, is the medicine helpful, is the intervention helpful? So I would do mu sub d greater than 0. And so here you calculate your sample mean of the differences, minus in this case, what's 0? The standard deviation of the differences, and this is really important. I've seen this mistake way too many times, and this is what I mean about thinking critically, right? If you're thinking about it, here I'm taking the mean of the differences. Why would I take the standard deviation of anything but the differences, right? That's what my statistic is all in relation to. It doesn't make sense to take the standard deviation of their performance on the test under placebo, or the standard deviation of their performance on the test under the intervention or medicine, right? I have to take the standard deviation of the differences. So it's like, if you think about my data in a tabular format, I have every student's performance under the placebo and then under the intervention. I had a third variable, a third column, which is the difference, and all of these are calculated under that third column, right? The mean, the standard deviation, and obviously n is the same because it's the number of rows, and that's the same for all columns, but you could also think of it as n sub d for consistency purposes. So obviously this is a lot easier, but it's also very different than the two-sample test for comparing means, and I want you to take a minute and think about what is the difference, besides the fact that this one's more complicated to calculate. In terms of application, when might I use Welch's test, or the two-sample t-test, or the paired t-test? And the response here, and I think it was hopefully clear in the examples I gave you, is that you are testing different things. So in this Welch's two-sample t-test, you're comparing, is the mean between the two groups similar? Whereas in the paired t-test, I'm testing, is the difference significant between the before and after, the treatment, so forth and so on? Is there a difference at all between the two groups? So it's much more detailed in terms of the interpretation. Here is just, are the means different? Whereas in the paired test, you're really comparing, are the distributions different? Are the differences between the variables different? And we'll go through some examples where we highlight this in more detail. All right, so I know we covered a lot of material. I have one practice question for you today, and then we'll do more practice questions at the start of tomorrow's lecture. So here's a practice question. Many of you may already know, normal body temperature is 98.6 degrees Fahrenheit. They randomly, right, this is one way to address the sample being representative of the population. They randomly tested 1,500 adults in Florida and got 98.2 degrees. It's close to 98.6, but different. Is it statistically significant, that difference? And further, you could argue that it's two-sided, but in this case it appears to be lower. So it's a left-tailed or one-sided test we're doing. We want to test, is the average body temperature lower for people in Florida, which sounds ridiculous, but these are the results we got, and we want to test that. And I put the research question in red here because this is an example of something you shouldn't do in practice. You should come up with your research question before collecting your data. Once you've collected your data, notice that there's a difference, right? You can comment on that in your EDA, your exploratory analysis, but you shouldn't change your research question as a result, right? Because that is a type of bias. Actually, it's not really a type of bias. It's more you're letting the data influence what you were going to test. And like, it could be due to random variation, or it could be a significant difference, but you should come up with your theory of what you want to test before collecting that data so that you're not influenced by something that may or may not be a true effect. So the first question for you is, what type of test is this? And then the second question is, do we do the one sample test, which is what we covered early on, the very simple t-statistic, the two sample, also known as Welch's, or the paired sample test? And we're going to do more examples so you get more practice with this. So take some time to think of those two things, and then we'll go over the answer. So the first thing you should do when you have a question like this is write the null and alternative. Right? The null is that the true temperature, the population parameter of body temperature for people living in Florida is 98.6, and the alternative, if it's one-sided, is 98.6. This is a left-tailed, one-sided test because we're only testing one direction. And I left this in red because you should not let your data influence your research question, right? You should come up with your research question before looking at your data. And now, should you perform a one sample, two sample, or paired sample test, hopefully you realized we don't even have a choice here. There is only one sample. If we had the body temperature of people who lived outside of Florida, you could make a case for a paired test or a two sample test. But we don't. We only have people living in Florida. We're going to plug in 98.6 here, right? In the two sample test, right, you have two sample means, right? And in the paired test, you have the mean of the differences, right? So you need a group A and a group B that you're subtracting either the means or the individual values of. And I would argue, even if you did have data of people living outside of Florida, it doesn't quite make sense to do a paired test because there's no natural pairing, right? There's no like, this person who lives in Florida, I'm going to compare to this person who lives outside of Florida. Like, why not some other person who lives outside Florida? Like, how do I come up with who I'm pairing together when I calculate those differences? And there are some approaches that you'll learn about in more advanced classes about how you do that pairing to come up with more accurate estimates. However, in this case, because there is no natural pairing, if you did have that data of people who lived outside, I would do Welch's test, the 2-sample test. Oops, sorry about that. 2-sample test where I compare the mean of people in Florida with the mean of people outside of Florida. Again, we don't have any data on people outside of Florida, so it's just going to be the mean of people in Florida minus 98.6 over the standard deviation of people in Florida over the square root of n, and then you'll get t. And we'll go over more detail how you go from converting your t statistic to a p-value, but you do have the intuition behind it, which we'll flip back to really quick. It's just you find your t, and then you look at all the values more extreme and calculate the probability under the t distribution. Okay, so that I believe is it for today. I know we covered a ton of material. We will do more practice questions in the future, and yeah, this is really important, really foundational stuff. We're gonna do other types of tests in the future, so please let me know of any questions. I'm happy to review it. We do have extra time budgeted in the semester, and we could go through more examples. I just need that feedback from you as far as what was clear. Thank you for your time. See you guys tomorrow.